Now, if you have not followed any of my lectures in the first two courses, or lecture sets that I've given, first on finite groups in pure math, and the second on quantum mechanics in mathematical physics, you may not be familiar with my format. I tend to sit because the second quarter of the board, the whiteboard that I'm using, so here, is too low for me to stoop. It's not comfortable, so I just sit on a chair, and then halfway through the session I reverse the direction of the chair and continue on. Right, so this second session for this board, 4 sessions per board, 4 quarters if you like, so 2 squares is just 1 square, so two squares per session, and 8 squares per board, so that's 4 sessions. Right, so this session will probably be fairly quick because I've pretty well covered most of the material in the first session, which was quite a bit longer than usual. Right, so yes, I gave the example before as well, 2 examples. One, a particular type of problem that can be solved that's easy, and that was an example was sorting numbers into order, increasing or decreasing order, numerical order. And an example of a difficult one was scheduling, like classes. Somebody, like pretty well every university, some poor slob is confronted with the problem of scheduling the classrooms, and you're not to have 2 classes take place in the same room at the same time. Right? That would be a clash. So I guess nowadays there are companies that schedule. I'm not sure. I've never actually been involved in that kind of thing. So maybe some of you know more about that than I do. How do universities? I mean, I've been a prof for years, but how the universities I've worked in, how they allocated their classrooms for a semester. I don't know. Did they use private companies to do that for them, or do they have their own people inside the computer science department that solve that problem for them? Anyway, it's a huge problem, right? And a lot of research done on that to try to get more efficient solutions to the problem, because it's a tough problem. It's one of the hard problems, and to get higher quality solutions, so like less clashes, so that human beings do not have to correct the so-called solution of the computer software, and rearrange things so that the clashes are removed. So, there are 2 examples. So what is it about a hard problem that makes it different from an easier problem? Like why the hard problems often require hugely more computing time than the simple ones. Right? So one of the questions of complexity theory asks is, well, what makes some problems computationally hard, like difficult, and others easy? That's one of the main questions, central question of complexity theory. And the answer is we still don't really know. There's a famous problem, I'll mention it, and we'll talk about it somewhat in this course. The famous NP. Just a minute. It's been a while since I've done this. The P. It has been a while. I'll forget it. I won't find it quicker. But the basic answer to this question is still not known. Right? There's a famous problem in computer science that tries to figure out whether a certain category of problems are truly difficult or not, or whether they could be simplified with sufficient ingenuity, and the answer is just not known. There's no mathematical proof to that particular problem, and that problem, I'm forgetting, without being able to find quickly the label of that problem, we will discuss in this course to some extent, right? So there's no, we still don't know the answer to the essence of what makes a problem hard or easy, or very hard versus hard, that kind of thing. Okay. So now CT, complexity theory, that's me saying that just for short. There's one of the things it does, it tries to classify problems into various levels of hardness. Right? So in a sense you can classify computer problems in that way, and each category of level of difficulty gets its own label. So we're talking things like P, like something can be solved in polynomial time, and NP, and NP hard, and so on. I'm jumping ahead, but you will learn these categories of levels of difficulty in this course. Right? So you can classify your hard problems, or level of difficulty type problems. Some are easy, some the so-called P, polynomial time. Don't worry about what that is. We'll cover that later. So the text, Sipser, makes the analogy that just as the chemists classified elements, the different kinds of atoms, the elements, in the famous chemical table. The main guy behind that was the Russian guy Mendeleev. You probably heard that name if you studied chemistry at high school. So by analogy, computer scientists have been able to classify problems into various levels of hardness and given them a label. And you will become familiar with those labels and how to classify problems into these various categories yourself. And that will help you actually in your practical computing life. I just found from my own experience. I've taught this course several times, once in the US, I think twice in China. And I just found that by knowing the theory, it helps your thinking when it comes to your programming. So if you're a programmer, having a good dose of theory under your belt, it helps your programming design. You can say, oh, you don't want to do that because that would then make it a certain category type problem, which is very difficult to solve, rather than a different approach, which makes things easier. And so, in practical terms, it's quite helpful. But you won't see that, and you need to go through the mill first. But I think when you come out of it, once you've finished this course, you'll find that the theory is not just airy-fairy, useless stuff. It becomes quite useful at times. Not always, but at times. All right. Now, here's a statement might be useful. Now, this classification scheme, dividing the problems into various levels of difficulty or hardness in their solution. So that this classification scheme, that it helps you show that certain types of problems are computationally hard. By analogy, that you can sort of, in a sense, map one type of a problem into another one, and if the other one is known to be computationally very hard, well, then you've learned something about your first one, because they're equivalent. So if the second one is very hard, therefore the first one must be very hard. That kind of thing. So you get evidence using this classification scheme for levels of hardness that that other problems, like new problems that you're confronted with, if you can map them to known problems and whose level of hardness is known, that can be helpful, allowing you to classify the new problem. Right? Okay, but you can't prove that this new problem is of a given level of difficulty, of hardness. Okay, okay, change tack a little bit. So, if you're a programmer and say you know a bit of computer theory, complexity theory, for example, and you start smelling that the problem you're working on, oh, this looks like a hard problem. Hard, not just in the ordinary difficult, ordinary man in the street type meaning of difficult. In this context, hard tends to take on a technical meaning, meaning computationally demanding, requires lots of time, a lot of effort on the part of the computer, lots of cycles to find the solution to, right? In that sense of hard. So if you're confronted with a hard problem, what do you do? So the text mentions that you have several options. I need to turn my chair around. So, what do you do when you're confronted with a difficult problem? Do you just give up? Do you just accept that it's going to take a zillion years to solve? What are your options? What can you do? So here are 4 suggestions the text gives, and I guess why does the author talk about this? What's the point? Well, I suppose he's trying to motivate your... well, I'm just guessing. I don't really know. I'm just reading between the lines a bit. I assume he's trying to motivate you to get more interested in the topic, complexity theory. Because as a programmer, if you're a programmer, this is your daily work. You come across